Hello, everyone, and welcome to Chapter 2, Section 8. So, we've done a lot in this chapter. We're still trying to remember what we've worked on. This time, we're going to work on a couple things called literal equations and dimensional analysis. Fancy words for simple processes. So, we looked at solving equations in all different kinds to include variables on each side. Now we're going to look at solving equations for a variable. So we won't actually get a number as our solution. We'll just get a variable answer, an expression, and that expression will either be correct or not correct. So we'll use some formulas, also with some real-world context, to understand how these things are in play. So we'll look at some equations. This dimensional analysis just means we're going to solve for a variable. And let's jump into that. So our first example here asks us to solve this expression, this equation here, for b. So what that means is we want to move this equation around so that we get b by itself on one side of our equation, one side of the equal bar, and everything else on the other side. So think about what's here. So we have to get rid of this 12c term. We also need to get rid of the 5. So this 12c is connected by addition. So what do we have to do to get rid of it? The opposite of addition. So we're going to keep doing what we've learned with these problems. Do the opposite of whatever operation is there. So first, write your original equation. Next, we can get rid of this 12c. It's just being added, so we'll subtract it away from both sides. If we subtract that 12c, on the left, these cancel out. On the right side, we get 9 minus 12c. So we're good on that step. Notice here, now we just have 5b. The 12c is gone. Now that 12c is over here and it's negative. So now we need to divide both sides by 5 to get b alone, because these are tied by multiplication. The opposite of multiplication is always division. So we'll divide both sides by 5. On the left, the 5s will cancel out here, so we'll get just b. And we'll be left with this expression on the right. Notice the 5 divided everything on the right side, not just one term. Division is going to apply to everything over here. So b equals 9 minus 12c divided by 5. That is our expression, our equation, solved for the variable b. This is our solution. That's all we're doing here. Can you do algebra? Can you solve for a variable and get an expression? That's it. We're not going to get just one number. We're not evaluating. We're just shuffling around the expression. So this expression that we got is our solution to 1a. So 1b, we want to get y by itself this time. We're looking for y. So we need to get this alone. So we need to get rid of everything else and solve for that variable. So if I rewrite my original, this is our equation. Now I know I want to get y alone eventually. I want to get this by itself. So I know that I can get rid of this 2x by subtracting it away. Since the 2x is positive, and I can do that on both sides. So 2x subtracted by 2x is going to be 0. So this goes away, we get just 0. So we'll be left with negative 17y on the left and negative 2x plus 13 on the right. So we have that. Now we still want to get y alone. So this negative 17 that's tied to our y, that's just a number. We can divide it away. So divide both sides by that negative 17. This will go away. And over here we'll do the same thing. So we should get just y on the left, and it will equal, if we break the 17 out into two different pieces, so we divide here and divide there and just add them together. Negative 2 divided by negative 17. The negative over negative just cancels out, so it's a positive. So that's 2x over 17. And then 13 divided by negative 17 is a negative value. So I'll put a minus. I would put a minus 13 over 17. So if we look at those steps, our solution is going to end up as C. So when we shuffle these things around, this is what we get as our solution. That is our variable solved for, our equation solved for y. Okay, so example 2a. We can now solve for x in this expression. So we don't need to worry about what the other variables are doing. We just want x by itself, just x. So I know I'm going to need to add 2z to both sides and then eventually divide away that 7. So first step, what is our original equation? Next step, we need to think about what can we get rid of. I know here I can get rid of this negative 2z thing. All I have to do is add the opposite to both sides. So add 2z here, and that will go away. We do have an x on both sides, so we can deal with this term as well. So one other step we could do is add xy to both sides. So if we do that, this will cancel out on the right, and we'll get an xy over here. So that's one step. We can simplify. This cancels out over here, so now we have this expression. Next, we could add that 2z to both sides. So on the left, you see we have a negative, a positive 2. Those cancel out. On the right, we just add it on, just tack it on there. And we get this expression now. So we're doing a couple steps. We're working through it. Now, the next thing we want to do is use the distributive property. So what do these terms both have in common? They both have an x. So we can pull that x out of both of those terms, write what's left in parentheses, that's 7 and that y, have them added together, and then just leave the x out here, multiplying both of those things. So you can see how this is the same thing, 7x, and xy. So we take out what they have in common, and now to finally get this x by itself, remembering we need this x by itself, we have to divide away this 7 plus y thing. We don't want that. So we divide both sides by 7 plus y. It'll cancel out over here, and over here we'll get an expression. So divide both sides by 7 plus y, and we get this expression as a final answer after all those steps to this problem. We solve for that variable. We got x by itself. So that one had many steps. Most of them will be a little bit shorter than that. But either way, you have to do whatever it takes to get your variable by itself. And it's always possible. So there's our expression. Also, as a side note, something to remember, you can never divide by 0. So anytime if you have a variable in the denominator, any value of that variable that would make the denominator 0 can't be true. So in this case, y could not be negative 7. Because 7 minus 7 would be 0. And we can absolutely never divide by 0 in math. So that's just something to remember as we do these problems. Okay, so looking at another example, here we want to focus on the variable a. So we're going to have to do steps just like last time. So there's a. So let's rewrite our original. 12a plus 3c is equal to 2ab plus 6. Okay. So I know I need to get the a's together so that I can eventually get them alone. So I will subtract 2ab from both sides. Minus 2ab. So on this side, I'll get 12a minus 2ab plus 3c. Notice none of these terms can combine. This is just an a, this is an a and a b, and this is a c. We can't magically add these together and say that this is 10 or 13. We can't do that. These are different terms, so we just leave it. Here, the two ABs cancel out. We get just 6. So I know I need the A's alone, but this 3C isn't helping me. I don't need that on the same side as my A's. So I will subtract that away. So whatever we do to one side, we have to do the other, of course. So here, the 3C's go away. And on the right, notice again, we can't just magically say, oh, this is 3C. This is a term that has a variable. This is just a number. We cannot combine them. So that's just 6 minus 3C. Now here on the left, we've got A in both terms. So what we need to do to get A alone eventually is to bring out an A from both terms. So we'll take out what both terms have in common, 1A, and then we'll leave what's in there, 12 minus 2B. Okay, so we took an A away from here and here, brought it on the outside, left everything else. That's the hardest step here. And the last thing we need to do is to divide away everything here in parentheses so we can finally get that A by itself. So we'll divide both sides by this 12 minus 2B expression. So on the left, that will go away. And on the right, we'll get this here. So A, this is gone now. So A equals this whole expression here. So do we have any answer choices that look like that? Well, these don't look right. This is not the right sign. So it looks to me like A is our best bet here. 6 minus 3C divided by 12 minus 2B. Okay, looks good. It says B cannot be 6, and that's because 12 minus 2 times 6 is just 12 minus 12. So what would we get in that denominator if B was 6? It'd be a 0, and 0 is not allowed as a divisor. So A is our solution with those steps. Move it around, think about it, get your variable alone, so we're good to go on that one. So here's a real-world example to think about. They say a car's fuel economy, given by E, is represented by this formula, E equals M over G. So please don't worry about all the words on this one. Just write the problem number and the formula. So the formula we're starting with is E equals M over G. Let's label everything. So M is the number of miles, G is the number of gallons, and we want to solve the formula for M. So that just means move these variables around until we get M by itself. So this is very, very, very easy. All we need to do is multiply both sides by G, and that will get M alone. Because G over G would just be 1, that would cancel out. And we get E times G on the left and just M on the right. So there's our beginning. With one step, we multiply both sides by G. Now G divided by G is just 1, so this allows us to cross those out and only get M on the right. So our answer to this problem is simply just M equals EG. All we did, one step, get M by itself by multiplying both sides by G. So now that we have this equation, we can look at applying it with an equation with real numbers in it. So M equals EG, so we know that. So the part 2 of this same problem, since we know that now, M equals EG. If Quanah's car has an average fuel consumption of 30 miles per gallon and she used 9.5 gallons, how far did she drive? Well, we have our formula for miles driven, and we know miles driven is equal to E times G. So E, her efficiency, 30 miles per gallon. So E replaced with 30. And her G, the number of gallons she used, is given to be 9.5. So we plug both of those in there and we multiply them. So M, in one step, check this in a calculator or by hand, equals 285. So what does that mean in the context of this problem? It means she drove 285 miles. There we go. Just a couple steps. That's our solution. Real world example of applying fuel economy as a way to understand this dimensional analysis, solving for a variable. Okay, example 4. The fourth type of thing we'll use is to understand how to change our units and keep everything equal. So for this one, the average weight of a chimp at a zoo is given to be 52 kilograms. So the name of the game for this example is, can you change units properly by setting it up and multiplying by what things are equal to? So if you've taken a chemistry class, they do these exact same things with units all the time. If not, this is something you'll see. So kilograms is what we start with, but we want to know what's the weight of a chimpanzee in pounds. In other words, we have to start with kilograms and somehow end with pounds by knowing a way to change these units. So how many kilograms will be in pounds? And we can separate those out and think about it as we get closer and closer to from kilograms to pounds. They also tell us 1 gram is 0.0353 ounces. So don't worry too much about the numbers. We can all put that in a calculator or multiply it through. So to start, what are we given? 52 kilograms. We know kilo means 1,000. So 1,000 regular grams is the same as 1 kilogram. This is 1,000 times bigger, so it's equal to 1,000 smaller grams. So 52 kilograms times 1,000 grams over 1 kilogram. That would allow us to go from kilograms to grams. We multiply by 1,000. Notice the units. Kilograms divided by kilograms, that would cross out those units. Now we have grams. So how would we get from grams closer to pounds? Next thing would be ounces. So how could we get from grams to ounces? Well, we just said here 1 gram is this decimal for ounces. So that decimal for ounces over 1 gram is how we'll go from grams to ounces. So in other words, if we multiply by this decimal, that converts our grams to ounces. Gram divided by gram cancels out. And now we're at ounces. Now with one more step, we can get to pounds. So how many ounces are in a pound? This is common. A lot of people know this. 1 pound is equal to 16 ounces. We see that here. So if we divide by 16, our ounces go away, and now we have the measurement for pounds. So with this setup, we went from kilograms to grams, ounces, and now pounds. So we can now see this is happening, and we can now have a unit in pounds. All of this needs to be multiplied or divided through, and then we'll get our final answer. So 52 times 1,000 times this decimal, divide by 16, then you get your final answer of a chimpanzee's weight in pounds. So we notice all our units cancel, and we're left with pounds. We get this decimal here. So if you estimate, that chimpanzee weighs about 115 pounds. So that's not too far off what you should expect. So that's our solution there. Just converting units. Very, very useful in the future to make sure you understand and get the correct answer with problems that have complex units. Okay, so one more example looking at this dimensional analysis type problem. So Janet is walking 20 laps on a track in a relay race to raise money for cancer research. Each lap she does is 350 meters. We want to know how many miles will she walk. So we're starting with meters. We want to get to miles. So we can get from meters to yards, and we can get from yards to miles. So let's start with what we know. So she's doing 20 laps on a track. Each lap is 350 meters. So 20 times 350 is going to give me the total number of meters. So 20 laps, we don't need to put the units, it's just 20 times this many meters. It's going to give us more meters. So that should be 7,000, and we can check that. So 7,000 meters. That's going to be our starting point for this problem. 20 laps on the track is 7,000 meters if each lap is 350. So 7,000 meters. Now, how do we get from meters? We want to end up with miles. So we can go from meters to yards here. I know 1 meter is 1.094 yards given here. So if I take the 7,000, I know 1 meter is equal to 1.094 yards. Okay, so in other words, if I multiply by 1.094, I'll convert my 7,000 meters into yards. The meter over meter cancels out, so now we have yards. But we don't want yards, we want miles. So how do we convert yards to miles? Oh, look, we have a nice conversion right here. 1 mile is over 1,700 yards, so we can use that number. So extend this out. I need to put yards on the bottom so that it cancels out, yards divided by yards. So I'll put that big number here. And I'll put that mile on top, 1 mile. So, meters would cancel out, yards would cancel out. We'd be left with miles as our unit here. So 7,000, you can do this in a calculator now. 7,000 times 1.094 divided by 1,760 will give us our final answer in miles. How far is 7,000 meters when converted to miles? And you can check this in your calculator. Our final answer will be 4.35 miles. That's how far she ran on the track. Makes sense, and she made some money for her charity for cancer research, so great cause as well. So hopefully you get that. You'll be good to go as we work further in this section.